Hello, in today's video we're covering orbital mechanics problems from the 1992 AP Physics Mechanics exam. This one dives into elliptical orbits, mechanical energy, and angular momentum, and even escape speed. Given that a spacecraft has 1,000 kilograms and it's an elliptic orbit around the Earth, at point A we find that it's 1.2 times 10 to the 7th meters away from the center of the Earth, and at point B we find that it's 3.6 times 10 to the 7th power meters away. We're given that velocity of at point A is equal to 7 times 10 to the 3rd power, and so on, as we can see below. Our first question asks us to find the total mechanical energy of our satellite at point A. So we're gonna move on to the next slide here. So let's start by writing the definition for mechanical energy is equal to, it's going to be our potential energy since the object can fall, and then its kinetic energy, which is its velocity. So we're going to start by writing what those mean. So we know that our kinetic velocity will just be 1/2 times the mass of the satellite and its velocity squared. We're given these, so that should be pretty easy. But we come into an issue when we try to figure out our potential energy, because we're given that we can find potential energy when it's mass times gravity times height, but gravity changes depending on how close you are to the center. So now that leaves us in an issue that we need to find a potential energy that changes with the radius from the center to Earth. So we need to start by finding a variable. So we know from our orbits equations, we're given that the force of towards the center, or at least between the two objects, is equal to, and you're gonna have G big M, which is gonna be the Earth, little m is going to be satellite over velocity squared. And if you know that if you take the integral of the force, we're going to get the, with respect to meters, which is going to be the radius, it's going to give us our potential energy. We know that if you just look at the units, potential energy is kilograms over meter squared over second squared, and force is kilograms over meters over second squared. And if we take an integral with respect to meters, we should get back to our potential energy. So that works out pretty great. So let's start by writing our integral. So we know that it's going to be going from infinity, so this out infinity in space, and then we have our radius, which is the radius of the Earth, from the center of the Earth to our satellite, and then we're going to take the integral of our force with respect to the radius dr. Now let's plug in our function that we're going to integrate on, which is going to be g, which is our gravity constant, mass times little m, and then we have our velocity squared. So we know that the gravity constant, the two masses, they're just constants since our variable is radius in this equation. So we're just going to move this out. So potential energy equals G big M little m, and it's just going to be the integral of 1/x squared, which is pretty simple. Which it's going to give us we're going to write our variables outside. Let's just move this down below actually. So this is going to give us potential energy equals Gm little m, and then we're going to write this as -1/r, and then we're going to integrate from infinity to our radius. And this process we're going to is just to answer how do we find the potential energy for varying gravitational force, and this is how you would do it. Now we know that we can simplify this because we know if you plug in r, you're just going to get 1 over r negative. But if you plug in negative 1 over infinity, it's going to go infinity to 0. So we can just write that as 0. So we're going to have g over big M, little m, over r, and this is going to be negative here. So since this work is done by gravity, the potential energy is going to be negative of work. It also reflects that potential energy decreases with the distance between them, meaning the satellite and the Earth, which is pretty like you can see that the potential energy is not going to be as great if the object's super far away. Alright, and then this is going to be your equation for finding the total mechanical energy. You should also take note of this equation for varying potential energy, as it's going to come around pretty often in these orbit questions. Now our next step is just going to be plugging and chugging pretty much. So if we go back to our last page, or we can just recall that the mass of our satellite is 1,000 kilograms, and the speed is going to be 7.1 times 10 to the third power meters over seconds squared. This will give us newtons, as we can see. And then we're going to minus our force constant, which is going to be 6.6 times 10 to the negative 11 power newtons kilograms squared over second squared. And then we should get, okay, I recalled why that's wrong. The units are meters squared over kilograms squared on the bottom, because we're going to have two masses on the top. And this equation is going to go off to the next slide, or a little bit lower most likely. We know that the mass of the Earth is around 6 times 10 to the 23rd power, 24th power. And then we're going to fill this in with kilograms. And then we're going to multiply it again with the mass of the satellite, which is 1,000 kilograms as before. And then we're going to divide this by, the radius between them, which is going to be, at point A, it's going to be 1.2 times 10 to the 7 power meters. So we're going to notice that these kind of get down to a measurement of newtons, which is what we're looking for. And we're just going to write the answer here. If you like to plug this into your calculator and see what you get, do it right now, because the answer is going to be 8.115 times 10 to the power of 9 newtons. And our example here, so this is the total mechanical energy in our problem. Now, we're going to solve, our next problem we're going to solve for is asking us, what is the angular momentum when the spacecraft is at point A? Since this is, we'll go back to our previous slide, at point A, since the velocity is like perpendicular with the position vector, we know we can use our angular momentum equation, which is equal to the mass times the radius and the velocity. But then I also asked the question, where do we get this equation? Because you're not always given this right away, and it's always good to know how do we get from here. So in our next, we're going to erase this slide, and what angular momentum is it measures how much rotational motion does an object have, and basically how it wants to keep spinning. And now it's going to be notated as, this is what you're going to be familiar with. The rotational inertia equals the dot product between the inertia and the rotational velocity. And we know that when it comes to masses orbiting at a distance r, we know that the I is going to be equal to mass times radius squared, which is familiar if we did those problems of finding the center of inertia. And we know that our velocity of angular velocity is velocity over radius squared. So now we're going to plug this in so we can use the units that we've been given. So it's going to be little m times radius squared over v over r squared, which is going to cancel out the bottom one. And we're just given with little mass times radius velocity. And that's how we derive our equation for angular momentum for rotating bodies. This is also another useful equation to write down, as it will come up many times even outside of this. Now let's just plug in the variables now that we have our equation. So the mass of the satellite is 1,000 kilograms times the radius in between them, which is 1.2 times 10 to the 7th power of meters, times our velocity, which is 7.1 times 10 to the 3rd, and this is going to be meters over seconds. And feel free to plug this in, because the answer is going to be 8.52 times 10 to the 13 kilograms over meters squared over seconds. So this is angular momentum. Now that we calculated this at point A, we can use this idea of the conservation of angular momentum. Because the object has no external torque, the angular momentum at point A will be equal to the angular momentum at point B. And our next question asks us, what is the velocity of the satellite at point B? If we go back to here, we know that we're going to have the mass, and we know the radius of point B. Now you're just left with, what is the velocity of the satellite at that speed? And that's our next question. So we're going to have to keep our answer here ideally. We'll just erase the first half of our problem here and move this up to the top, since we're going to be using our result again. And we know this is going to be 13 kilograms. So let's use this idea to find our answer for the velocity of point B. You can also use your equations from a body orbiting in elliptic orbits. If you have that in your notes, there'll be a second way to double check. I'll just give you the equation for that. So we know the angular momentum for point A already, which is going to be the radius at A and times the velocity A is equal to the satellite mass times the distance between the Earth center and the satellite times the velocity. And now we know that the masses cancel out, but we're not gonna cancel them out since I guess we can, why not? So we're gonna write we're gonna solve for V of B, which is gonna be R of A times RA divided by RB, which is going to give us a value. If we now we just need to plug and chug, which is going to give us the radius, which is going to be around 1.2 times 10, something like that, times 10 to the 7th power. This is going to be the radius. And then our velocity, which is 7.1 times 10 to the 3rd power meters seconds, all divided by 3.6 times 10 to the 7 meters. And this is going to give us a velocity at point B for the satellite equal to 2.37 times 10 to the 3rd power meters per second squared. So it looks like if you got this, that means our numbers are checking out. Now you can also use our velocity equation for elliptic orbits to double check your answer. especially during the test, it can be pretty useful. So we know that the velocity of elliptic orbits is equal to the 2g up here, which is going to be our gravitational constant, and it's going to be our the mass of the Earth divided by, this is going to be the radius of where we're trying to find our velocity at, times 1 plus the velocity where we're trying to find at, and then the other side radius if it's given, and this will give you the velocity at that position of elliptic orbit. Note that the gravitational constant is equal to 6 times 6, 7 times 10 to the negative 11th newtons meters squared over kilograms squared. And that should check out for this section. Now our next question asks, what is the circular orbit speed? Because in our scenario, the spaceship or the satellite speeds up at point A and gets into a circular orbit and is no longer in a elliptic orbit, which if you're traveling a satellite and trying to get out of the orbit of the Earth, you would speed up at point B, because it's one of the most like efficient ways of getting out of the orbit of the planet is you get into these elliptic orbits and then speed up at the furthest point to generate a larger circular motion. Now we can just erase most of this as we don't need it anymore. It wants us now, so now that the satellite is in a circular orbit, this will be a very easy calculation. So we just know it's the gravitational constant over the mass of the Earth divided by the radius squared. And we're just going to solve it by just plugging and chugging. So these last two ones are going to be really simple. It's just knowing your formulas for the most part. This is going to be gravitational constant, newtons, kilograms over meters squared. You should feel free to derive these last two equations, as they can take a lot longer to do. This will be most likely covered in a different video. Times the mass of the Earth, which is 6 times 10 to the 24th power over kilograms, and it's all going to be over the radius from those 2 points, which is going to be around like, I don't know, it's around like 1.2 times 10 to the 7th power at point A. This is when the object or the satellite is going to speed up, which gives us a velocity of around 2.37 times 10 to the 3rd meter second. So this is as expected, and it seems to check out. Now our next question asks us, what is the escape velocity? So the idea of the escape velocity is that the object needs to accelerate 140%, around 100% of its orbit velocity, and this will send us out of the planet pretty much, which is going to be just the square root of 2 times our gravitational constant times the mass of the Earth radius, and this will give us the escape velocity, which is another really great formula just to have written down. And once you calculate that, the velocity escape is just equal to 8.17 times 10 to the 3rd meters squared. And thank you for watching my video today, and if this helped you out in some way, please like and subscribe so you can motivate me to continue these type of videos. And thank you for watching again.